welcome back. This is second session of elementary number theory. We will first start with a couple of applications of divisibility thing results which we proved last time, because they are very important. And the second thing is we will go to division algorithm. So I will title this as divisibility 2 and division algorithm 1. Okay, let's get started. Right, I have not taken my pen. So, do you remember one of the first important things, if we saw that if D divides A and let us say and D divides B, then we show that D divides XA plus YB or same as ADX plus BY for every XY in Z. Okay, this is a very useful result. Okay, in particular it says D divides A plus B, D divides A minus B, and D divides A squared, etc, 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 right? So to make sure that whenever divisibility problem comes, you should think of these things. I'll give some 2 or 3 typical examples. Okay, what are they? The first example application is that suppose I have a polynomial ax squared plus bx plus c, okay, equal to 0, right? So suppose these are all a, b, c are all integers. Suppose d is also an integer, so that okay, d is a root of this polynomial. Okay, that is ad squared plus bd plus c equal to 0, right? Then we want to prove d divides c, right? It's totally easy, because if you know your algebra, then you can write it as x minus d into x minus e or some such thing and try to compute, etc. But we want to use divisibility test. Okay, this is a very well known result in theory of equations. Whenever d is a root, then okay, d must divide the constant term. Okay, that kind of thing. Okay, something similar. Okay, that is it. But this one is easy, because notice that ad squared plus bd plus c equal to 0. That means c equal to minus of ad squared plus bd. That is, it is d times minus ad plus b, if you want minus b. Yeah. Therefore d divides the LHS, right, RHS, and therefore d divides c. Why does it divide? We already wrote that. Okay, and we saw that we write it as d times this. Even otherwise, you know that c is going to be this, but since d divides minus ad squared, d divides bd, then d divides a plus b. You understand that? D divides a, d divides b, then d divides a plus b. So d divides minus ad squared and d divides minus bd, therefore d divides the sum, which is c. But I directly proved c equal to d times some integers. These are all integers. Okay, they are all integers. Okay, make sure that in our divisibility is within the field, within, when I say field, okay, if you know the word field you may get confused, within the realm, within the context of integers. Okay, is it okay? Pause, review, proceed. And second example is this. See, I saw a problem. It's some kind of a mini Olympiad problem possibly. Okay, find a factor, a divisor, a positive divisor, d of, okay, such that d is greater than 1 and d is a divisor of 7571 and 5311, right? Again, if you remember your high school thing, you tried to factorize into primes, etc, etc. You may do that, but let's try to tackle this problem using division algorithm, division thing. Okay, divisibility problems. properties. You okay, there may be much smarter way, I do not know. As I said, I am not great in number theory. Okay, mine is very conceptual understanding, but as I said, there are a lot of challenging Olympiad type problems in number theory which I am not good at. Okay, so you may be able to find a smarter solution. See, if D is a divisor of this, then I know D must divide, okay, plus, okay, any linear combination, that is A times, sorry, X times this number 7571 plus Y times this number 5311, right? But easier thing is, I know it should divide X minus Y and X plus Y, and it's easier to find divisor, okay, of a smaller number. You understand? These are my thinking. Therefore, D must divide 75 minus 71 minus 5311. So I hope that is 63 and 3, this is 2 and 22260. Yeah, is that clear? Right? Now again this the number is small, and you can immediately see there is a kind of 10 divides this. Therefore what I have is, that is 2226, right? Therefore 10 should divide this, but 2 also divide this, therefore 113. So 113 looks like a prime number. We have not introduced prime number yet. Okay, I am just making use of your knowledge about prime numbers, right? Because 11 squared is already 121. Okay, so anything before this, and it should be a prime, so it should divide this 2, 3, 5, 7. That's it. These things do not divide, you can see. Anyway, 113. So my guess is, does 113 divide was 7571, and 113 divides 5311. This is just for illustrative purpose, so it's a hit or miss. Okay, right. So let us see that 7571 113. This is a long division I am doing, so I think I can go up to 6 times. 6 times will be 8, 1, then 6, 7, and 6. Right, therefore that is going to be 9, this is going to be 7, 751. The obvious thing will be 7, 7 times will be 91, 7, yeah. And similarly 5311, 113, this must be 4 times will be 52, right? Let me see, is it 4 times or 3 times? 4 times will be 52, 4 and 52, I think that should be right. So this will be 52, and this will be 4, therefore that is going to be 9, and this is 2, therefore it is 7. So it's the same thing. I'm happy. You understand that? Notice that when D divides A, D divides B, that implies D divides A minus B, therefore it's a divisor of A minus B. We are not claiming, we do not claim. Okay, D divides A minus B implies D divides A, D divides B. So we do not know, it is a hit or miss. Please understand the logic carefully. Okay, because if I take A equal to B, you understand, and then, are you following? So A minus B will be 0. Therefore any integer D, okay, divides 0, right? If D is any non-zero integer, then D divides always 0. Therefore can I take something? Therefore can I claim D divides A, D divides B? I can't do that. Okay, am I confusing? Please play this video again and understand. So it's only necessary condition, so it's a hit or miss. Somebody wanted me to find a common divisor of this, which is greater than 1. Okay, so how do I do that? The easiest thing is I look at something, divisor of some smaller number. If you divides this, then D divides this. But as you can see, if D divides this, I am just trying to find something smaller factor. The smaller factor turns out to be 113. Okay, how did I do that? Again, it's a purely lucky hit. Please understand. And the third problem is, for every natural number n, you want to say the fraction 21n plus 4 by 14n plus 3, okay, is in reduced form. Do you know when do you say a fraction p by q is reduced form? There exists no common factor, that is there is no common divisor. You understand? Therefore what all I have to show is there is no common divisor greater than 1 of both the numbers 21n plus and 14n plus 3. You understand this problem? Yeah? How do I tackle this kind of thing? Because this is for any natural number, so how am I going to find a common divisor of 21n plus 4, 14n plus 3? You understand the problem? So this is where our thing comes. So what I have to look at? I will look at some 21n plus 4 and then 14n y times 14n plus 3. Right? So again remember what I want? I want something less. Right? Please pay attention. This is 21n plus 4 and this is 14n plus 3. So obvious thing is some multiple of this and minus this, or the other way around, this minus this. You understand? Now you can see the easiest way to knock off is 21 times 2 is 42, 14 times 3 is 42. Therefore that gives me an idea, and if I multiply this by 3 I am going to get 9. If I multiply by this 2 I am going to get 8. Therefore what will I do is I will take 3 times 14n plus 3 minus 2 times 21n plus 4. So if t is a common divisor, right, then d should divide this, then d divides this. But what is this? This is 42n plus 9 minus 42n minus 8, which is equal to 1. Therefore d must divide 1. That means d equal to 1. Right? Therefore the only common factor for numerator and denominator is 1. Therefore it is in reduced form. Okay? Pause, review, proceed. You see that I gave three simple examples just to show the power. Okay, we had divisibility properties. One of the most important property in my opinion is if d divides a, d divides b, d divides ax plus by. In particular d divides a plus b and a minus b, etc. Right? So that is what we try to use it. Remember that this is a very important tool in divisibility problems. Okay? Right. Let's go to the next topic. So this is part of the divisibility 2 session. Now we are going to division algorithm. See, but division algorithm is a misnomer. It's a bad name. It's not a very correct name, because when you say algorithm, what does it mean? It gives you step by step so that you get the answer. Okay? But division algorithm is a theoretical result. It simply says the existence and uniqueness of something. Okay? Don't get confused. If you are a BSc student, don't feel intimidated. We are going to prove those things. State it very carefully. Explain that with something. Okay, we'll start the problem. Suppose, let us assume we are, several thousand years ago. Okay, so I am a human, you are a human. Okay, so now I want to I have 27, let us say, sheep, and I have 4 sons. Okay, I want to divide equally to them. Remember, those days I did not know anything about multiplication table, division, etc. So what do you think I will do? Try to think carefully. This is what we are going to do. Let us explain. In number theory they will not write. Immediately they will start with the proof. Let us try to do that. So 27 sheep. So this is my son, second son, third son, fourth son. So what will I do? After 27 sheep I will give one each sheep. Okay, one sheep to each. Then then I will count this I know. Okay, don't think of it as a division, what do you call, subtraction, etc. When I have given, then I will see there is something I can still give, so I will give some more. So I will, how many sheep I can give like that? I'll give one time, second time, third time, fourth time, fifth time, sixth time I'll give. Then what will I left with? So 23 so this will be 23 minus 4, that will be 19, then 19 minus 4, that will be 15, 15 minus 4, that will be 11, 11 minus 4, that will be 7, and 7 minus 4, it will be 3. Okay, this is the first time, second time, third time, fourth time, fifth time, sixth time, right? So I had given 6, this is 6. So everybody gets 6 equally, and I am left with 3. Okay, 3 sheep is for me and 6 sheep for each of my children. Right? Therefore what happened? 27 sheep I split it into 6 times 4, okay, plus 3. Okay, are you following? Now just because we know multiplication, tables, etc. and division, long division, you would immediately said it in your second or third standard. 27 divided by 4 is 6 is the quotient, okay, quotient or whatever it is, dividend, and 3 is the remainder. You understand? So this is what we want to prove. We want to prove, given A and B, A is a natural number, B is an integer, then what do I want to say? I can write BA as A times Q plus R. Okay, where Q is an integer, and what do I want? R? R should be 0 less than or less than A. Do you follow that? That is, you have given me B. If you want to think of B as again as a natural number for the time being, don't get confused, right? B equal to, I want to say AQ plus R. So as it is, whatever this R is called the remainder, and Q is called the quotient, right? So this R should be, I should not be able to divide further. We'll go back. After 6 times when I am done, what I am left with is 3 sheep. Then there is no way I can equally distribute to 4 of my children, right? So I stop there. So similarly I want to do that. So the division algorithm says the following. As I said, it's not an algorithm, it's the existence result. Given A, B and Z with A natural number, there exists unique integers Q and R such that 1. What is the first condition? B is AQ plus R, and second condition is this R is always positive and less than A. Do you understand this? And when I say unique, what is it unique? If you write B equal to some AQ1 plus R1, and that is also equal to AQ plus R, then I am claiming Q equal to Q1 and R equal to R1. That is what uniqueness means. Okay, so notice that it does not give you a method, stepwise method. If you give me an integer B, okay, how to find Q and how to find R. It does not give step. It only proves theoretical result. Okay, please understand this. So how will I do this? Okay, please go through this, understand the statement. That is very important. So how will I find this? Let us go back to our example. That is, I had 27, I wanted to divide by 4, I want to write 27 equal to 6 times, okay, if you want AQ, right? 4 times 6 plus 3. This is my A, this is my B, this is my Q, this is my R, right? So let us assume now to start with B is positive. Okay, remember, if B is 0, there is nothing to do that, because if B is 0, then my Q will be 0 and R will also be 0. Therefore I can assume B is non-zero. Okay, right. Now how will I do that? Let us go back what I explained. As a primitive man who did not know anything like multiplication, division, etc., what will I do is, from 27, okay, right, I have 27, then I will remove 1 4, then it is 23, and again I remove from that 27 minus 4 times 2, that is gives me 8, that is 20, 23 minus 4 19, yeah, and then 27 minus 4 times 3, 27 minus 4 times 3, okay, that is going to be again 15, then I keep on writing, you see that. So I have 27 and 23, 19 and 15 and 11, and then after 4 7, and after that 3, after that I will, when I subtract 4, that will be minus 1, and so on. You understand that? Yeah. So where did I find it? So the what is the remainder 3? Where do I find the remainder 3? So that is, in this set, it is the smallest positive natural number. Okay, here what will I do? Okay, I divided, so I can also do something else, right? So instead of subtracting 27 plus 4, 31, okay, and 27 plus 2 times 4 times 2, that is 8, therefore 35 and 39, I can keep going. You understand? It is an arithmetic progression. So I start with 27, keep on subtracting, okay, 23, 19, and keep on adding 31, 35, etc. So in this, so this list I can write it as, okay, b minus a k, where k is an integer, right? You understand this? This is what we did, okay, right? If k is minus 1, okay, k is plus 1, then what do I do? B minus a, then b minus 2a, etc. Please understand, this is b minus a, this is b minus a2, that is a times 2, this is b minus a times 3, and so on, therefore b minus ak, right? This is the set. In this set, my r turns out to be the smallest natural number. And how do I find my, this is 15, 11, right? Now how do I find my thing q? This is 1 times I got, okay, when I subtracted 4 1 times from 27, I got 23. This is 2 times, this is 3 times, this is 4 times, this is 5 times, this is 6 times. Therefore this is 6. This is how I find. Okay, please text, okay, pause, review, proceed. To understand this, try something else, okay. I will give a very small number, 17, okay, and 5. My b is 17 and a is 5. Do this, okay, do this process so that you will understand. Okay, the key to this, the important tool for this addition algorithm is so-called well ordering principle. This of natural numbers. What does it say? It says that if S is a non-empty set of natural numbers, then there exists an n in S, so that for all k in S, k is greater than equal to n. That means n is the least. So S has the least element, which is of course naturally the least element. So what are the conditions? I want S to be non-empty and S to be a subset of natural number. That's very, you can intuitively feel, right? I start, these are my natural numbers, okay, and collect some numbers arbitrarily, okay, that is my set S. Then do you believe intuitively it has a least element? That's what the axiom says. This is actually an axiom of one of the, okay, of natural numbers. This is equivalent to well ordering principle, but let's not worry about such things. Okay, just assume that. Okay. So what does well ordering principle says? Whenever I get a non-empty subset S of natural numbers, it has a least element. What does it mean? There is a natural number n that should be an element of S, and for every element k of S, what should be the relation between k and n? N should be less than or equal to k. That is how it is a least element. Yeah, please understand this, internalize this statement before we go further. Because the reason why I want this, you can see starting from 27, I have a lot of numbers, right? These are all the positive numbers, 27 plus 4, 20, then 31, 35, 39, 43, it keeps on going. In this set, what is the least natural number? Namely 3. That is my remainder. Okay? And similarly in this case also you will do the same thing. That is 17, 5, B is 17, A is 5. You will have 17, 17 minus 5 is 12, 12 minus 5 is 7, 7 minus 5 is 2, 17 plus 5 is 22, 22 plus 5 is 27, and so on. You will keep on going. In this set, what is the smallest number? That is 2. That we know. When I divide 17 by 7, then 17 is 7 times, sorry, by 5, that is 5 times 3 plus 2. Right? So we know 2 is a remainder, 3 is a quotient. Okay, that is also clear because 1, 2, third step I got it. Yeah. So I want to make sure there is a theorem. So let us start with the proof. So pause, review, proceed. So what we do is we construct a set S, which is, okay, the set of integers of the form b minus ak, where k is a natural number, k is an integer. Okay, notice that this is an arithmetic progression. The only thing is this arithmetic progression goes both sides. Going both sides. Okay, let us again look at the elements. This is b, b minus a, b minus 2a, b minus 3a, and so on. Here b plus a, b plus 2a, and b plus 3a, and so on. These are your S. Okay, you should internalize. You should not simply look at symbols. Right? So what I want to do, I want to say this set S has, okay, yeah, positive elements. No, that is non-negative elements, non-negative integers. Because I have to say non-negative, because if my b is, let's say 12, a is 4, then my q is 3 and r is 0. Right? Therefore, if I write down this, what should I find? My 12, this will be 12 minus 4, 8, 8 minus 4, 4, 4 minus 4, 0. So I will get 0. Right? So I should be claiming this. How? Why that is possible? Let us look at. Notice that if b is already, as I said, b is non-zero. Do you remember that? Suppose b is already a natural number, therefore b is either positive or b is negative. Therefore, since it's an integer, it has to be a natural number, right? If b is already positive, that element is there. Therefore, you understand? Let S plus be set of elements x in S so that x is greater than or equal to 0. I want to claim this set is non-empty. Okay, if b is a natural number, notice that b already is here, right? Therefore b belongs to this, therefore it's non-empty. Do you understand this? Yeah, okay. Suppose b is negative, what will I do? Okay, let us again look at some example, come back to this. So I want you to understand the proof. I am not trying to write a textbook proof at present. You follow that? Textbook will be only 4 line, 5 line, and students simply learn by heart. They do not understand why it worked. So let us do this. Suppose I have, let us say, minus 17 and divide by 5. Okay, my b is minus 17. A is 5. What does it mean? So I have minus 17. I want a positive thing. What should I do then? I have to add minus 1 times 5, right? I have to add 5. That is, this is minus 17 plus 5, okay, and minus 17, this is minus 12, therefore minus 12 plus 5, that is minus 7, and minus 7 plus 5, that will be minus 7 plus 5, that is going to be minus 2, and minus 2 plus 5 will be 3. Okay, you understand this? Again, you may get confused. Let me just give again an example. It's very important to understand mathematics conceptually, okay, not learn by heart. Okay, so think of this. I borrowed 17,000 rupees. Just think of 17 rupees. Okay, 17 rupees borrowed, you lend it. Okay, then what I do is every month I can pay you only 5 rupees. So how much money I have then? I have minus 17. That means that only says I owe you 17 rupees. Right? Now every month I have some earning, out of which I can pay you only 5 rupees every month. That is my EMI. Okay? So first month I gave 5 rupees. Then how much I owe you still? Minus 12. And second EMI? Okay? So minus 12 plus 5, that will be minus 7. And third EMI, that is minus 7 plus 5 will be minus 2. Can I stop here? No, I can't stop. I have to pay you full money. So fourth time also I will give EMI. Okay, I will give minus 2 plus 5, that means 3 rupees. That means you will give back my 3 rupees. Are you following? So minus 17 is going to be, therefore what do I have? So I am paying you back, right? Therefore 5 times minus 4 plus 3, that is minus 20 plus 3. Because remember my remainder R, therefore this is my Q, this is your A. This is, what does it minus 4 simply mean? It's not my money, I am paying you back. How many times I have to pay you back? 4 times, 4 EMIs I should pay you. If I pay you 4 EMIs, how much I have paid you? I have paid you 20 rupees. But then I owe you only 17, therefore what you will give me back? 3 rupees. You understand this? So let us go back. If B is negative, so I want to show S plus is non-empty, and B positive we already proved. Suppose B is negative, then what do I want? I want to say there exists an integer k such that B minus AK is greater than or equal to 0. It can even be greater than 0. You understand that? Right? That means B must be greater than AK. Yeah? You understand? Greater than or equal to if you want. But remember, B is positive. See, B is negative. Therefore, minus B is what I want to look at. Minus B is going to be less than or equal to minus AK, which I can write as A times minus K. Are you following? Now, A is positive. This is a natural number. Therefore, this is positive. And this side is positive. Therefore, minus K must also be positive. That means K must be negative. Do you understand this? Yeah? So, go slow. I want to choose an integer K such that B minus AK is greater than or equal to 0. If such a K exists, then B must be greater than or equal to AK. But remember, B is negative, so I want to look at, and I want to use A is positive, so let us look at minus B, therefore will be less than or equal to minus AK. That I can rewrite as A times minus K. Now A is positive, minus B is positive, therefore minus K must be positive. That means K must be negative integer. Do you see that? That's what we did. Okay. Now what integer I will choose? K, so that this will be greater than this. That is very easy. Remember, we already proved it. Okay, let us recall. Let me do some other number. Let us say T is a natural number. If T is greater than or equal to 1, then, and if K is any integer, then K times T is greater than or equal to K. right? So now do you see that? So if I take my k equal to b, then minus k equal to minus b, and since a is a natural number, a is greater than or equal to 1, minus b times a will be greater than or equal to minus b. Are you following? These kind of things are never worked out in the classroom. The teacher will simply say take k equal to this, b or minus b or mod b. He will go through the proof very fast. You may not realize. We are working. We are trying to understand why it works. So let's go back. So I know k must be negative. So what is the obvious thing? I also remember when t is greater than or equal to 1, for every, if you want, for every natural number m t is greater than or equal to m. Okay, so I want my something greater than or equal to minus b, which is positive number. Therefore, what is the obvious thing? Take minus b itself here. Therefore, if I take k equal to b, then minus k is minus b. Since a is greater than or equal to 1, multiply both sides of the inequality by positive number minus b. Then what do I get? Minus b is greater than or equal to minus b. Are you following? Yeah. Therefore this number minus a times minus b is in S, right? Yeah. And therefore a times minus b is greater than or equal to 0. That also we proved. Yeah. Sorry, b plus a times minus b is greater than or equal to 0. That's what we proved. Yeah. So what you have proved is S plus is not empty. If b is negative, then what we do? Take k equal to minus b, then b plus a k is b plus a times minus b, but that is b times 1 plus 1. Sorry, let me just make sure I am writing it correctly. Yeah, b plus a, right, k equal to minus b, therefore b plus a times minus b, therefore if we take b, that is 1 minus a. Yeah, and remember b is negative and a is greater than or equal to 1, therefore this is also negative, this is also negative, therefore this is greater than or equal to 0. Do you understand this? We struggled to get this, but a typical textbook proof will say, oh, okay, textbook proof, how will you try it? Okay, take k equal to minus b, then claim, okay, b plus ak is greater than or equal to 0. Why? That is b plus a times minus b, that is equal to b times 1 minus a, and this is negative, this is less than or equal to 0, therefore this is positive, greater than or equal to 0. Therefore we proved it. Yeah. So pause, review, proceed. Did you understand what we did? Okay. You look at some elementary number theory book, most often they will say, okay, take k equal to mod b and then try to manipulate. You may not even know how the teacher knew why the proof. Now we slowly worked out. When b is positive, we take b equal to b itself, k equal to b. Okay, I mean, we can take b itself is an element of S. If b is negative, then we take k equal to b or minus b, whatever. Okay, we got the result. Okay, I hope you understand this. Okay. So what I have shown? So we have shown that, okay, S is set of all integers of the form b minus ak, k is an integer, and S plus is, okay, S plus intersection, S is S intersection Z plus. That is set of all x in S, so that x is greater than or equal to 0. This is non-empty. Okay. Now if it is 0 is there, okay, then what does that mean? Okay, if 0 is there, then S plus has already a least element. Okay, you understand that? If 0 is there, that what does it mean? That is, for some integer k, there exists an integer k in Z such that b minus ak equal to 0, because 0 belong to that, right? If 0 belong to this, that means it must be here. That means b equal to ak, right? Therefore what is r? R is 0. Therefore I can write it as this, 0 less than or equal to r, which is less than a. You found it? Yeah. And suppose, okay, let r be the least element of S plus. So let us assume 0 is not in S plus. Okay. If 0 is not in S plus, that means, okay, there exists an x such that x is greater than 0, right? Therefore all my s, that means what does it mean? This means S plus is contained in natural numbers. Yeah? Right? Let's go back. Okay, it's best to learn mathematics rather than simply going line by line. Let's go back to the earlier example. Yeah, you saw that 17 free. Then my S plus consists of only these elements. There is no 0. After that, when I take minus, I will get a minus 3 and minus 8 and so on. You follow? This is the least element is 2. So everything is positive in S plus. Okay, therefore there exists. So when R belongs to S plus, what does it mean? Now R is in belong to S plus, but S plus is contained in S, right? Therefore what does that mean? Any element here is of the form b minus ak. So there exists a q, an integer, so that R is of the form b minus aq, right? So that R, that is b equal to aq plus r. So one part of the thing we found out. In the division algorithm, what are the 2 points we wanted to say? We wanted to say b is of the form a plus br, but then next we have to say r is lies between 0 less than or equal to r less than a. Yeah? Okay. Okay, so one is proved. Now let's look at 2. Suppose r, I want to say, that is, if you want to claim 0 less than or equal to r and less than a. Notice that our assumption is r is not equal to 0 and r belongs to S, therefore r is already greater than 0. R belongs to S plus, therefore r is greater than 0, right? Now suppose r is greater than a, greater than or equal to a, I want to claim, suppose I want to claim r is less than a, suppose not, then r is greater than or equal to a, right? But what is r? R is b minus aq, right? Therefore r minus a will be greater than or equal to 0. Yeah, therefore r minus a is r minus a equal to b minus aq minus a, that is b minus a into q plus 1. Okay, that is greater than or equal to 0, right? Now q is an integer, right? Therefore this is again an element in S and it's also an element in S plus. Yeah, r minus a is of the form b minus ak, right? And it is greater than or equal to 0, therefore it is an element of S plus. Okay, now do you see a contradiction? Then since a is positive, r minus a is strictly less than r, and this is an element of S plus, this is also an element of S plus, but r is the least element of S plus, right? So this contradiction shows r must be greater than or equal to a. Yeah, this is a contradiction. Right? R must be less than a. If r is greater than or equal to a, we arrived at a contradiction. Okay, therefore r must be less than a. We already know r belongs to S plus, therefore it is greater than or equal to 0. Therefore what I have shown? Therefore you have shown b equal to aq plus r, where r is between 0 less than or equal to r less than a. Okay, we have proved the existence part. So P or P. Now let us go to uniqueness. Suppose I have my B is AQ, let me write AQ1 plus R1 equal to AQ2 plus R2, and uniqueness is, remember, uniqueness is going to follow because of our specific condition on R1 and R2. Otherwise you notice that if I write 17, I can write it as 2 times 5 plus 7 or 3 times 5 plus 2, right? So this 7 is greater than 5, but my remainder should be strictly less than 5. You understand? That is where the uniqueness is going to come, right? Suppose this, then claim we want to prove Q1 is Q2 and R1 is R2. So what I said is, it's important to concentrate on the remainder now, not on the quotient Q. So I will first prove R1 is R2. Okay. Notice that 0 less than R1 less than A, 0 less than or equal to R2 less than A. Is it okay? Now if R1 is not equal to R2, remember R1, R2 are all integers. They all R1, R2, they all belong to integers, right? Okay. Therefore, one is strictly less than the other. So with a loss of generality, assume R2 is strictly greater than R1. You understand that? Okay. Now what is R2? R2 is B minus AQ2. What is R1? B minus AQ1, right? Now what do I know about R2 minus R1? R2 minus R1 is an integer, and since R2 is strictly greater than, yeah, R1, this is actually R2 minus R1 is a natural number, right? Now let us try to see what happens to R2 minus R1, right? Now R2 minus R1 is going to be, let us look at this. This is going to be this minus this, B minus B 0. This is will be A into Q1 minus Q2. Let me just make sure, yeah, A into Q1 minus Q2. Okay. Are you following? I am subtracting. I hope I did correctly. Yeah. Now what do I know about this? This is a natural number. In particular, it's positive. What do I know about this? This is again positive. It's a natural number. Therefore, what do I know about this? The product of two numbers is positive. Therefore, this must be positive. And these are all integers. Therefore, it must also be a natural number. Do you understand that? Q1 minus Q2 is a natural number. Right? Since Q1 minus Q2 is a natural number, this is greater than or equal to 1. And A is positive, therefore A times Q1 minus Q2 must be greater than or equal to A. Right? So this right side is greater than or equal to A, but let's look at the left side. R2 is already less than A, and from R2 you are taking R1, therefore A minus R1, right? R1 is greater than or equal to 0, therefore this will be less than or equal to A. Therefore R2 minus R2 minus R1 is strictly less than A. Are you following? R2 is less than A. From that I am subtracting R1, which is a non-negative quantity. Therefore this quantity will be strictly less than A. Yeah. So the left side is strictly less than A, whereas the right side is greater than or equal to A. So therefore that's a contradiction. So LHS is strictly less than A, RHS is greater than or equal to A contradiction. Therefore R1 must be equal to R2. If R1 is R2, then what do I get? Then B plus A, sorry, A equal to, what did I do? Yeah. So B equal to AQ1 plus R1, call it simply R, R1 equal to R2 equal to R, and equal to A into Q2 plus R, right? So now from this equate these two, therefore A into Q1 minus Q2 equal to 0. That is B minus, subtract B minus B, this will be 0, therefore this is 0, R minus R is 0, therefore this is 0. But A is not 0. A is a natural number, therefore A is not 0. That means Q1 minus Q2 is 0. That means Q1 equal to Q2. Therefore, you have proved R1 is R2 and Q1 is Q2. This proof is actually demanding. Okay. So since the time we have taken a lot of time, I would like you to go through this proof. Please remember, in a textbook you will see it only about 5 to 6 lines. Okay. You can only verify logically the proof is correct. You may not even know why people thought of that. Yes, how did they think of, they have to think of well ordering principle, and how do they think of R1 equal to R2 first, not Q1 equal to Q2. Okay, all these things. And sometimes they even take rational numbers to prove all these things. We don't need it. We proved everything within integers. Okay, please go through this proof carefully. In the next third session, third video, I will say how to write a textbook proof of this. Okay, but wait, okay, till then go through this proof at least once or twice. If you are a beginner BSc student, this is a fantastic proof to learn. Please do that. Okay, we will meet again.